Hi everyone, welcome to today's class. So for topic number 9, I have chosen one important topic from chemical thermodynamics, which is again a important chapter for CSIR-NET. Many questions are asked from this chapter, and this is obviously from physical chemistry. So in this video, you will understand some basics of thermodynamics and zeroth and first law of thermodynamics and the some basic thermodynamic parameters and all. So this lecture is important to understand overall thermodynamics and to solve the questions which are asked from the basics actually. So to have the knowledge is very good for the exam. Okay. So let's start today's topic. So first we will know about systems and surroundings. Okay. So what is system and surroundings? Let's start then. So let's see one room. Okay. Let's consider a room having this kind of various kind of shapes. Okay. So in this room, if I choose, I want to study about these shapes. Okay. So I am choosing this part. Okay. So this part I want to study from this room. Okay. So this part will be called now system. This will be called system. So let's see the definition now. System is the selected quantity of matters or a region of space which we want to study. Okay. If we are saying any system or something like that, so it means that we want to study that and there will be one boundary. This is actually boundary. Okay. Boundary. So this boundary can be real or imaginary. Both are possible. But we are considering a boundary is there which is actually separating the system from its surroundings. The other thing, the surroundings. Okay. So what is surroundings now? Surroundings are or surroundings is everything outside the system which we are not studying. We are studying a little bit of part. Other than that is the surroundings. Okay. Now boundary, I have talked about it. Surface that separates system from surroundings. Okay. And universe is systems plus surroundings. Means here universe will be the this kind of room or this whole structure. Okay. So now coming to the various kind of systems. Okay. So we drink coffee, right? No, not everybody. Many people like to drink tea. Okay, so we drink tea, coffee. If anyone doesn't like tea or coffee, hot water, hot water everybody drinks, right? So if we think we are thinking about, let's say, hot coffee or hot tea or anything, so here what is happening? So let's see here this kind of thing. So here we are here. Firstly, I have to tell you we are here defining systems on the basis of mass. If the mass is changing or not, and the energy. Okay, two things are there: mass and the energy of the system. Okay, so we have to see now that mass and energy are changing or not. Okay, in the systems. So here what is the system? This cup of tea or coffee, right? Because we are studying it. So here what is happening? It is open and this kind of vapors are there. Okay, so vapors are there means that vapors are going outside. So it means that in the vapor, inside the vapor, various water molecules are there. So which are the things of system, right? So here, as a steam, the water is going outside or going to surroundings. So here, the mass changing is there. Mass is transferring. Transferring of mass is there. Exchange of mass. Okay. And if we consider the heat, so after a certain time, let's say very hot coffee is there, we can't drink it. So we are keeping it as it is, and we wait till it cools down a bit. Then we can drink it, right? So why it cools down? Because it transfers energy to surroundings. Exchange of energy is there. So here, exchange of energy is also there. Okay, with example you will understand in a clear way, right? So this type of system is called open system. We will talk about it in the next slide also. So it is open, we can say. Okay, mass is also exchanging and energy is also. Next, okay, now we don't want that okay, everything is exchanged with the surroundings, transfers to the surroundings, so we don't want that. We take a lid which fits perfectly in that cup. Okay, so with that lid we cover the cup in a good way. Okay, so that it tightens the cup actually, so no vapor will go to outside there. So now mass changing is not there. So mass changing is not here, but energy change will be there, because this from this wall only, if you touch the wall of the glass or cup, you will find that it is hot. That means it is transferring heat to the surroundings. Fine. So this will be called, this kind of systems are called closed system. Okay. Now there are another kind of systems, isolated system, where so here mass and energy both were exchanging, and here only energy. So what will be here? Mass will be also constant and energy will be also constant. Okay, so it's not exchanging with surroundings means the system has the same mass which it has, which it had actually. So mass is not changing, mass and energy is constant for this system. Okay, so three kind of system we have understood with a coffee. Okay, coffee, hot coffee example. Okay, so this we can say uh, chai pe charcha or something like that. Okay, so now types of system. So open system, we have talked the open glass of coffee mug or coffee, and closed system and isolated system, right? So two parameters are there, mass and energy. Okay, so for the open system both are exchanging with surroundings. Okay, tick and tick. For the closed system, mass is not changing, right? Mass is constant, but energy is transferring to surroundings. Okay, for isolated system, both are actually conserved inside the system. For example, any thermoflux or where insulator walls are there, so that heat can't be transferred to the walls, the outer walls. Okay, so these kind of things are there. So with examples we have understood this. Next, thermodynamic processes. Okay, so various type of thermodynamic processes are there. So with the system, what we actually do, we will study the systems, right? So with what basis? So there are certain processes. So it will be mentioned in the question that isothermal process is going on. So you have to remember that in isothermal process, what is the characteristics of this kind of process? Here T is constant, means dt will be 0. There is no change of temperature. Okay. Next, adiabatic process. Adiabatic means Q is constant. Q is heat. Heat of the system will be constant. Isobaric process means P is constant. P is pressure. And isoporic process, here V is constant. V means volume. Volume of the system is constant. So this kind of process you should remember, because in the questions itself, and for the derivation part also. So if somewhere it is written that it is isobaric process means pressure, you have to understand that P will be not changed. Okay. So here I think you know these kind of things. Next will be the reversible and irreversible process. So what is a reversible process? It can occur in both directions, forward and backward. Okay, like if you say A to B is happening, the changing, this kind of arrow will be used for the case of reversible process, where A to B is going on, and at the same time B also converted to A. Okay, so when actually the both rate will be same, like on what rate A is changing to B, and which is equal to the rate of changing of B to A, that time we can say that the system is in equilibrium. So reversible process is going towards the equilibrium. Okay, so this kind of arrow is used here, where it can occur in both direction, forward and backward. But for the irreversible process, it is the opposite of it. So it can occur in only one direction. One directional change is there, and this kind of arrow is used. Okay. So here, the second point is system and environment can be restored its initial position. What does it mean? It means that when reversible process is going on, some changes or a little bit changes, if we try, or if we apply a little change of the conditions, we can have the backward process in such a way that we can get the system and the environment, uh, uh, the initial position of system and environment can be restored. Okay, so before the reaction, what was the position, or what was the amount, or uh, all the conditions of a system will be restored actually. Okay, but here it is not, it is opposite. Here it is not, cannot be restored. Okay, it is a ideal process. It is said that any natural process in reversible way, it is not possible actually. Okay, but it is real process. So inside our body, the enzymatic reactions and everything is going on, right? So here, this kind of these processes all are irreversible kind of process. Okay. So, and reversible process, it is very slow, because you can understand that forward and backward reaction both are going on. Okay. So it is very slow process, and it takes infinite time for completion. And here it is a fast process. It takes finite time for completion. Okay, so it will be also this kind of the idea of reversible and irreversible will be also helpful when we solve the question, and when we derive various formulas. Okay, so now we will come to the intensive and extensive properties. We are now reading the or understanding the basics of thermodynamics. So this kind of knowledge, these kind of terms you should understand. Okay. So what is intensive and what is extensive properties? Intensive properties, it is only one thing you should remember here: mass independent, mass dependent. Sometimes students actually are confused about this too. So for easy to remember, it will be easy to remember if you can read like that way, that intensive, in and independent. So intensive property, for the case of intensive property, it will be mass independent. Like that way I can remember this also, because it is very confusing, I know. So in and in, right? So I think it will be helpful for you to remember. Now the examples, it is independent of mass. When we are changing or when we are varying the mass of the system, it will not change actually. Okay, and some properties are there where mass changing actually have a high impact in that properties. Okay, so mass independent properties are temperature, pressure, viscosity, density, molar volume, energy, enthalpy, free energy, etc. And here energy, volume, surface area, enthalpy, etc. Extensive means depends on mass. Okay, and one important thing, if you see that molar volume, okay, just one important thing here is the ratio of two extensive properties will be always intensive. Means the if we take the ratio of two extensive, two mass dependent property, that will be independent of mass or intensive property. For example, if we take the density is where? Density is an intensive property, right? Density. And what is a density? It is actually mass by volume, and mass is obviously extensive depending on mass, and volume is also a extensive property. So both are extensive, Ex and Ex, but their ratio density will be IN, intensive. Okay, so another examples are also here. If you see that molar volume, okay, volume is extensive, enthalpy is also extensive property, and free energy is also extensive property, which means they depend on mass. But when we take the molar term, that time this all quantity will be independent of mass. How? So this is molar. This will be for 1 mole of the 1 mole, for 1 mole the volume will be. Okay, so molar volume, actually molar things are defined by, let's say one volume of the system is given and we want to know the molar volume of that system. That time what we should do? We should take the volume of the system and the molar volume of 1 mole, sorry. So we should take the volume for 1 mole of substance, Vm. That will be the molar volume of the overall system. Okay, so both are extensive properties, and when we take the ratios, it will be intensive. For every cases, this is happening. Okay, this is an important thing you should remember. Now, coming to the state function and path function. This is again very important thing, and sometimes questions are asked directly from this, which are state function and which are path functions, like that way. Okay, so this is very important. So just look at the important points. If we try to learn this, some important points we have to remember. For the state function first, it is single valued thermodynamic function, obviously, and its magnitude depends on only the state of the system, initial and final. It doesn't depend upon the manner of change, how the changing is happening. Okay, so you are confused maybe. So I will show you an example, then you will understand it clearly. Okay, so state function. Let's see. Let's say let's say graph. If I take PV graph, no, I will take simple real life example. Okay, so let's say this. This is a point. This is a point. Okay. So A, B, and C. This is the house of A. Okay. A is a person, a boy or girl. So he is going towards C's house. Okay. C actually C invites him or her. So he will go to C's house. Okay. So there are various way from which A can go. So he is going through, let's say, from this path. First, it goes to B's house and uh, talk to him a little bit of for a little bit of time, and then it goes to C. Okay, but when we talk about the distance of A to C, the A's house and B's house, the distance will be this one. Distance will not depending on the how A actually comes to his house, right? So like that way, if we think that any process for any process, so a process is actually going on, and we want to calculate the, let's say, this one. Okay, so let's say if any process is going on and which is first go to this way, going to this way, like the previous examples I have taken. Okay, it is going towards first sorry, let's say this one is B. Okay, this is B, this is A, this is C. Okay, so for a process, the changing is the path is first A to B and then B to C. Okay, this kind of process, one process is going on from A to B, B to C. Okay, just like that. But we want to now, we want to know about the, let's say, work. Okay, change of work in this process. So what we will do? So work is actually depends on the path, how it changes. This will be path function work. So it depends on A to C. A to C changes there, or A to B and then B to C changes there. Okay. So W and Q will depend on this. But there are some properties, for example, enthalpy, entropy, internal energy, which are which which doesn't want to know that A goes to first B and then coming to C. They doesn't want to know about all these things. They just want to know when A was at A point, what was its quantity, like what was its enthalpy, let's say. Okay, and at the point C, what it has, what its enthalpy is. So let's say H2. So it only depends on, for the all the state functions, the change actually depends on the final minus initial. How much change is happening? It depends on only the quantity or the value of the initial and the final. Okay, so change will be delta H will be H2 minus H1. But for the case of when we read about the path function, the thermodynamic quantity that depends upon the path taken by the process to reach the final state. Like the same I have told you, like A to B first it is going on going towards A to B and then goes to A to C. So you have to calculate first, let's say work and heat are generally considered as path function. So for work, let's say from A to B work is W1 and B to C the work is W2. So work will be, total work for this process will be W1 plus W2. So it depends on how it is actually changing how the path actually, not that the initial and final. So path is not important there. It can be circular path, it can be zigzag, okay. But for the path function, it depends on it going to a zigzag manner or a simple linear fashion. This kind of things are there for the path function. Okay, so you should remember the examples that work and heat. Work and heat are not depending on the final and initial state of matter. Okay, so it depends on the path, which path it is followed. Okay? So for a, let's say, now we are considering a cyclic process. Important. For a complete cyclic process, the state function is zero and path function will be non-zero. Let's take an example. Okay, so you are thinking like this right now. So let's say a starting running from a process starts actually. So from A to it comes to A again. Okay, so this is a cyclic process. Let's first consider the state function. State function, for state function we want to know the initial and final state, not the path. Okay, so it is initial and final state is again A. So the initial and final is same here. All the properties of initial state will be same for final also. Let's say it is a graph P and V. So in this point, the P and V values are same, right? So here change of the state function will be final minus initial, right? For every state function. So here it will be 0. But for work, if you consider work or heat, it will not depend on initial or final state. It will not see that, oh, okay, I was at A point and again I am coming to A point. So net work will be 0. No, nothing like that. Because if we are running, let's say you are running, okay? So your energy will be lost, right? So you have done some work, you were running, okay, for this path, this circular path. So this circular path you were running. So some work you have done, obviously. So that is the kind of thing that path functions are followed. Clear? So for the cyclic process, state function will be 0 and path function will be non-zero. Clear? Now coming to the thermodynamic laws. So first it is zeroth law of thermodynamics. What it is? So it is simple. If let's say A is in thermodynamic equilibrium with B and B in thermodynamic equilibrium with C, then what will happen? A will be in equilibrium with C. If we take an example, let's say A is a friend of B. A and B are friends and B and C are friends. Okay, B and C are friends. So A will think that B is my friend and C is friend, right? So he is also my friend. Like that way. A is also my friend. So like that way, zeroth law of thermodynamics actually going on. Let's say one system is in equilibrium with B, thermal equilibrium or anything. Okay, thermal equilibrium. A is in thermal equilibrium with B and B is in thermal equilibrium with C. Then A will be in equilibrium, thermal equilibrium with C. This is called the zeroth law of thermodynamics. Okay. Now the first law of thermodynamics. So before going to the first law of thermodynamics, we should know about what is the internal energy of a system. Okay. So internal energy is a state function and extensive property. Okay. State function means not path, state function. It depends on the state, the final and initial. And extensive means mass dependent. Okay? Okay. But what is actually the internal energy? The sum of all the molecular kinetic energies and potential energy. So if for a system we want to know about its internal energy, we should have an idea of its kinetic energy and potential energy. So both, the sum of both will be the internal energy of the system. So U will be total energy of a system, kinetic plus potential. Okay. So in the potential energy itself, there are actually, let's say, if the one system is constant or it is not moving, okay, so kinetic energy will be zero, but it has potential energy due to the vibration inside the thing. There are molecules, so there will be the vibrational motion, rotational motion, and electrical also will be, electrical energy also will be there. Also E electrical plus E vibrational plus E motion. So E means energy due to the electron transfer between the electronic states, vibrational motion, electronic motion, vibrational motion, and the rotational motion. Okay. Energy of rotation. Okay. So these kind of things are there. So to know the internal energy, you have to have the idea about all the values of system. But we for a system to have the all the values of this kind of energies will be difficult. Okay. So for that reason, there comes the first law of thermodynamics. This is nothing but the conservation of energy, which we actually have read about. We all know this, that energy cannot be created, cannot be destroyed. So energy conversion of energy will be there, but energy can't be destroyed. Okay. So this is called the conservation of energy. So it is nothing but a conservation of energy. Like if, let's say, in a system the internal energy was UA. Okay. And now we are giving uh, some heat to the system. Okay. So delta Q amount of heat is given to the system. Then let's say after giving the heat, the system will do some work. System will do, or the surroundings, the work will be uh, by the system or on the system. Okay. So some amount of work is there. Okay. So then the UA will be equal to UB, because now internal energy will be changed and we know the energy is conserved. So system is given some heat, actually it uses that heat for work. So dq is there and dw is there. So this is the main thing of first law of thermodynamics, that UA was the internal energy of the system, UB is the internal energy of the system after the giving the heat, and after giving the heat, the system, let's say, uh, work have done the work. Okay, dw work, amount of work. So that time for the conservation of energy, U wave will be UB plus dq plus dw. Okay. So this is the mathematical form of the first law of thermodynamics. So you should not forget it. du equals to dw plus dq, where du is change in internal energy, dq is change in heat, and dw is work done. So it can be both ways: work done by the system, work done on the system, right? And our IPAC convention of work is, when work done by the system, their time negative sign is there, we should use negative sign, and work done on the system is, if it is there, surroundings are actually involved in the working in that system. So that time work will be positive. Like that way, na, work done by the system. Let's say we are paying the electric bill, or we are actually our money is lost, means work done by me, work done by the system. Okay, money is given by me, and work done on the system, someone gives you money. So the change is in your system, in your money. Like money is lost and money is restored, but the positive sign is there when work done on the system. You are having some money by the surroundings, and work done by the system when you are paying some money, that is negative sign, right? So if the volume of the system increases, work done by the system. So for this, when you actually consider that okay, work is done by the system or on the system, what is going on actually? So it is not like that you are counting money and okay, so money is lost, money is not like previous, it is less than the previous amount of money. So work done by me. Okay, but in the system, inside the system, it is not like that, na? So if the volume of the system increases, that time we can say work done by the system. If the volume of system decreases, work done on the system decreases. So you should remember it like that way, that work done on the system means, if it is a system, surroundings is doing work on that. Okay, so let's say pressure is given. Okay, so volume is decreasing. Like that way you can remember these things. And dw is considered, we will talk about in the other lecture, but you should know that work is minus pdv, where p is the pressure and dv is the volume change. And if the volume of the system increases, work done by the system, that time dv will be positive, right? And so dw will be negative. And we know that negative dw means work done by the system. Same way. So these two are actually matching. This one and this one. Okay. And if volume of the system decreases, if volume of the system decreases, that time it means that dv is negative. So work which is minus pdv and dv is negative, so it will be positive, which means work done on the system. And positive work means work done on the system. So both ways it actually matches. Now, first law of thermodynamics, we know that du equals to dw plus dq. So let's say for adiabatic process, you remember, right? For adiabatic, what is constant? dq. The heat is constant. dq equal to 0. Okay. So how this first law formula will change? If we put the value, du will be dw, right? So for adiabatic process, du will be equal to dw. For isothermal process, isothermal, here in the name only, you can understand it will be dt equal to 0. Temperature is constant. Means temperature is constant. So here, what will be here? Here no temperature term is there, but after a few lecture, we will, I think in the next lecture only, we will understand that for the isothermal process, du will be 0. You can actually imagine that isothermal means that temperature is not changing. So at first U1 amount of internal energy was in the system, and we have said that when some amount of heat is given to the system, that time system is doing some work, and this kind of equation are there. But here isothermal process is there. So no change in temperature is there. So that time du will be same. Okay. So in the next lecture only, we will understand that. So for the isothermal process, what will be now the equation? dW equal to minus. Okay. This is the equation for isothermal. This is for adiabatic. You don't have to remember anything. Just remember the for this kind of specific process, what will be constant. So that you can put the values there. Some parts of it or some portion will be cut down, and then the rest of it will be the equation. For cyclic process, what will be the equation? We know for the cyclic process, state functions are 0. The change of state function, right? And here, internal energy, work and heat is there. So we know W and Q are path function. W and Q path function, and U is state function. So du will be 0 for cyclic process. So same like isothermal process, here will be dW equal to minus dQ, right? And for isobaric process, what will be here? Isobaric process, dP equal to 0. Yes. Yes, for isobaric process, dP is 0. So here also you have not read it actually. So in the next slide only, you can understand what is enthalpy. So enthalpy is the dP isobaric, right? So delta U plus PdV. Okay. So delta U plus PdV is there. Constant heat. Okay, no, VDP. So it will be VDP. Yes, almost forgot it. Okay. So delta U plus VDP is there. So as dP is 0, that time delta H will be delta equal to delta U. So for isobaric process, that will be the equation. You will understand in the next slide only. And for the isochoric process means dV equal to 0. Isochoric means volume is 0, right? And here du equal to dW plus dQ, and we know dW is minus PdV. So here dV is 0 means dW is also 0. So that time du will be equal to dQ. Okay, these are some important equations. You don't have to remember anything, just remember that what is constant for the specific kind of process. Okay. Now coming to the enthalpy, which I was talking about, it is a state function and also extensive property, and this is important. So when in a system PV mechanical work is done on the system, that time the total the PV mechanical work plus the internal energy of the system is called the enthalpy of the system, right? So these are the terms here. P is the pressure, P is the volume, and U is the, you know that internal energy. So when delta H is positive, that time it is called endothermic reaction. and when delta is negative, it is called exothermic reaction. Okay, so I think you know this, because when we are seeing any reaction is happening, if reactant is here and product is here, right? So this kind of, with this kind of graph, actually reaction is happening with the Ts. So this change is called actually the enthalpy change of the reaction. It is Hp minus Hr, right? If it is positive, that time we say that it is endothermic. When it will be positive, here in this case, which I have drawn, it is positive or negative? You tell me. It is energy, right? So energy of P is less than energy of R, so it will be negative, obviously. So it is a exothermic reaction case. And if I draw like this way, let's say this is product, this is reactant, and the reaction is going on with this pathway. So now delta H will be positive, right? Because now delta Hp has greater value than Hr. So that time we can say it is endothermic reaction. Endothermic. So this is for the general knowledge, because this kind of terms and the signs you should know. Now again the enthalpy. Why we are studying this again? Because we know now enthalpy is what is enthalpy, right? But we have to derive the further formulas from it. Okay. So if we take d both side derivative, dh will be du plus d pv. The changes actually. D means change, small change. So from here we can write, if we separate these two, this is uv kind of thing, right? duv. So for this, what was the formula? First we have to keep one constant and the derivative of other. Then we have to keep the second one constant and derivative of the first one. Okay, like that way. So here if we apply this here, so first b will be constant and dp is there, and then p will be constant and rest is dv, right? Next, this one also we can write from where? From where it is coming? We know that for ideal gas equation, PV equal to energy. This we all know, right? So just I am putting here the PV value as energy, and in this term, in this whole term, R and T are constant because temperature of a system is constant here. We are not saying that temperature is changing, and R is obviously constant. This is gas constant. So here this will be the equation. Delta N is the changing factor, or it will only change between the reactant and product, but RT is constant. Okay. So if we consider here isobaric, here in this now isobaric means constant pressure, dp will be 0, and if we put dp 0 here, so like previously in the previous slide I have talked about previous, or that the first law equation, that's right. So dp is 0, so du plus vdv, which means from the first law we know that du equal to dw plus dq, and we know dw is minus vdv. Fine. If we put the value pdv plus dq, right? du equal to, so dq will be du plus pdv, right? So here we can put dq, From this uh, one definition of DH or enthalpy is enthalpy change is there like that way, that at constant pressure change in heat change in a process is the enthalpy of the enthalpy change. Actually enthalpy change will be there, change, enthalpy change the system. Clear? Now coming to the question. So you all understood the what is the enthalpy, what is uh, the internal energy of the system, first law of thermodynamics. Okay. So now coming to few questions from CSIR-NET. So this is from CSIR-NET June 2017, which is saying that the correct statement from for any cyclic thermodynamic process is. Okay. So we have read it, right? So for state function, and in the cyclic process, state function will be actually 0. So we have to find out that what is here the state function, right? So this will be dq, this is path function. W and q are path function. This will be not a state function. So this will be not 0. So these two are actually not happening. du, we know that this is internal energy change, which is a state function. It depends on the temperature of the system, right? So it will be in the cyclic process. The cyclic process it will be 0. This is correct. Here we have find the correct option, but let's see here what is happening. This is b dq. This is nothing but b is constant. B will be will come to the outside, and this integration has the dq. This is like that only. First option. So it will also not be the correct one. So correct answer will be C. Next question. This is from gate 2010. Okay. So I hope you understand that. This is war, this is Q, this is internal energy, this is entropy. Entropy you have not read it, but let's see other factors here. So W and Q, okay? W and Q is here. We know that these are path functions, right? It depends on the path. So W and Q are path functions where it is given. Here, see, we don't have to know about here only the entropy and what is internal energy. So if we know only the what are the path functions, the rest we can find out. Okay. So D will be here correct answer. So now, so that is all for the first portion of the thermodynamics. This is the basics. Actually, I have talked in a simple manner so that you can understand. I have taken simple examples so that you can relate the things and understand in a better way. So I hope you have understood it and you have found the lecture interesting. And in the next part of the thermodynamics, we took the various questions. From the this part, actually not much questions are there, but this part is important for the understanding of the whole chapter. So that's why I have started with that this for the thermodynamics. So I will come with the another lecture of thermodynamics. Okay. So thank you so much for listening. We'll see you in the next class. Thank you.